Welcome to lecture 15 already of quantum physics for non-physicists. Today is the 3rd of October. Where's October gone? There you go. November, sorry. That's why it's gone. 3rd of November, and we'll finish for now with this stationary states in 1D. So there's only one missing of the ones we'll do now, which is having a particle in a box, but the box is finite size, which is something you did in the tutorial already, so I'll go over it relatively quickly. And then we're going to make a pause on what we've been doing so far, which is like solving explicit potentials. And we'll talk about something much more general, which is how we model uncertainty, information, and ignorance in quantum physics. And this is a very useful tool in general in quantum information theory, in quantum computing. For physics in general, it's the density matrix formalism. We'll talk about the partial trace and maybe a little bit more about evolution of states like this. And the daily analogy is something that will be useful today, which is this idea of a trick that is used a lot in physics teaching. And this is more or less like when you're watching a detective story and then you see Sherlock Holmes making a leap of logic that turns out to be right, but she could never have guessed it at a time, like if he was a real person, right? And sometimes there's problems in physics that we go through the problem and we know like the standard way to solve it, and then someone tells us, oh, but there's a trick, here it is. And I don't want you to feel like, oh, I don't know any physics if I don't know this trick, because the way it comes about is that people have looked at this problem for a very, very long time, and then after doing this kind of things for a long time, you start developing some intuition. So don't worry if you have this intuition yet. Which means from now on, whenever there is one of these tricks, I'll put this little drawing of Sherlock Holmes, so you know that it's that's what it is. That, you know, there's other ways to solve it, but this is kind of the clever way, which is obvious in retrospect. Good. So let's just see more or less where we are. So we were looking mostly at dynamics for the last few weeks. We looked at first circuits, rotating spins, measurements in discrete systems. Then we looked at continuous systems, at this Herrenfest theorem, the free particle, the particle that's free but inside a box. We looked at applications in physics, like this experiment where you couple two systems, the spin and the position of a particle. We looked at the double slit experiment, modular momentum, that has the evolution of a superposition of free particles. And then we looked at stationary states in 1D for some very simple potentials, right? So today we will finish that with the finite well, and maybe we'll come back to this kind of problems later on when we look at 3D problems. But for now, we want to start with this part of the lecture, which is talking about uncertainty and ignorance. We will talk first about how we model this at the level of states. Then we'll talk about how we model uncertainty at the level of evolution. Later, we'll talk about entropy measures, so measures of uncertainty. And then after all of this, we'll talk about uncertainty relations, which is something that is usually introduced much, much earlier, but I think we'll have a better understanding of what it is after some formalism. And some very nice application of this is quantum thermodynamics, which we'll see. Maybe we'll give one lecture too. Very good. So what did we do last time? We looked at this idea of the finite barrier, right? This was a barrier that looked like this, chuk, 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 chuk. And we saw that there were two cases when the energy of the particle was below this top of the potential. Then we had some tunneling. And when the energy of the particle was above, so the particle propagated, the wave function propagated like a wave. I don't want to say this. Also inside the barrier, and then there were some scattering resonance frequencies, okay, at which there was more wave being transmitted from one side to the other. Okay, and this corresponded precisely, just like in the finite box case, to the case where the wavelength inside here is like double times the size of this box times some number, right? So it corresponds to this kind of modes where chuk, chuk, chuk. where the particle has the same value here and here. The wave function has the same value there and there. Good. So, and the main insight from this is this kind of discrete behavior of quantum systems, right? That you do get these peaks at discrete points. It's not all like a boring function. Okay. Let's go with boring, and I'll remember the word later on. Okay. And now we will look today at the last of these cases, which is the square well. And this was case number 3. So this means a finite box. Okay. And what does it look like? Well, this is X, this is V, and we're going to draw it in particular here. Now, of course, the choice of coordinates is arbitrary, right? We could very easily have put the box here or there or there, and we choose these ones because then the problem looks kind of symmetric, and then we can apply some tricks. So in this case, we have that V of X is what? It's V0 when X or minus X is larger than A, and 0 if small in this region. Up. Okay. And again, depending on where the energy of the particle is, if it's here, then you get this kind of scattering state. But we're going to look at cases where the energy of the particle is below this top of the potential, because they are the more interesting ones. Okay, so we're going to look only at bound states, which means that energy of the particle is more than V0. So what we know from it's a bounded interaction zone, so we know the behavior of the particle in all the regions. We just need to glue them together, right? So E, Px for x smaller than minus z, decays exponentially there. And then it has some B, E, I, Kx, x in the middle, and it's going to be some D, E minus Bx. So it's going to look like this. So here it will decay exponentially on this area and on this area. It could have a different constant, but it has the same decay rate. And then here somehow it will be a superposition of a wave going this way and a wave going that way with the same period. And again, they could in principle have different constants behind it and the relative phase, etc. What are this B and K's? Just like before, we saw that they just depend on the energy of the particle and the potential. E, B is square root of 2 mu B0 minus E over h bar square. Okay, and now this is where we're going to use the clever trick. Which is just to look at it and say, well, this looks like a very symmetric problem. We cleverly put this box like just around 0. There's a minus A here, plus A here. The Hamiltonian is very symmetric. What did we look at some point that looked like we could exploit this symmetry? Well, in the tutorial, you look at the parity operator. I don't know if you remember this. It's acted like this. So this is the operator P, not the momentum parity operator, okay. And it acted in this way that when x on x, it returns minus x. Okay. And because H is symmetric, around x equals 0, in particular, it will commute with this parity operator. Okay. So monotonic is the word I was looking for. Boring before. See, it always comes back here. It's not a monotonic function, it's a function that has this peaks. That's the word I was looking for. Good. Good. So H is symmetric around x0. You can do the maths and see that this is indeed true, that P commutes with H. We looked at some point at the, I think in the tutorial, we did the matrix representation of this operator P, or continuous matrix representation of P. And if you plug in our H, in this case, you're going to see that it commutes with P. But what does it mean that it commutes with P? Well, then this means that, you know, we can diagonalize them in the same basis, which means that they share the same eigenstates. And remember, we're looking for stationary states, which are eigenstates of the Hamiltonian. Now we know that the eigenstates of the Hamiltonian are the same as the eigenstates of the parity operator, just with different eigenvalues. And what we know about the eigenstates of the parity operator, well, we know that they have two forms. So these are symmetric states and anti-symmetric states. Which means f of x equals, sorry, the wave function is the wave function of minus x and anti-symmetric. And this is when psi of x equals minus psi of minus x. Okay, which means what? It means that we can look here and simplify this a lot, because we only need to have cases where b and c are either the same or the same with a minus sign. Okay, and again, this is kind of, if you're given this, then okay, it's obvious, but getting there for the first time might not be so simple. Okay, and what else do we know? Well, A and D must also be the same up to a sign difference, right? Okay. So let's look first at the cases of even parity. So you look first at the symmetric case. So one. Case, meaning psi of x equals psi of minus x. So how do we simplify that function there? Well, you have a, sorry, a exponential of bx. Then here you have b. If these two are the same, if this is the same as that, then you have e ikx plus e minus ikx, which is just the cosine, right, up to a constant factor. So you get some b cosine of kx, and then you get a e minus bx. And this is for x more than minus a, x in the middle, and x larger than a. Okay. And now what we need to do, we need to do the continuity. We need to still group together these functions. So we do just like before, continuity, continuity. And you see, like, this is always the same procedure, but the insights we gain are different depending on the case, on the potential, so it's worth doing it. Sorry, x equals a. It's going to be the same for x equals a or x equals minus a because the problem is so symmetric. Okay, so this must be continuous, meaning what? A e bx equals b cosine of kx. Sorry. A minus b a. It's better. And the first derivative must also be continuous, as we saw before. Because the potential is finite, so we get what? Minus b a e minus b a equals k b minus derivative of cosine is minus sine k a. Okay. And in addition to all of this, there's also a normalization of the wave function, by which I mean one is this. Okay. So from here, you can already get A and B up to a phase, up to a global phase. So still, we have these two equations. What we're going to do with them? And again, are you still here? You're still here. What we do with them is call this equation 1, call this equation 2. What we do is divide one by the other. Okay. And again, it's not the first thing maybe you think of looking at it, but it's something that works. So we do this, and what we get? Well, the minus signs can cancel out on both sides. The a's cancel out, the b's cancel out. So all we get, and this exponential cancels out. So what we get is b equals k, and then sine divided by the cosine is the tangent, right? Of ka. Okay. And in fact, you can even put the k on this side. Okay. Now, a is a constant, b is a constant, only k is the only variable, which means that we have here like two functions, which you could try to plot. We'll not succeed at plotting them, but then I'll show you a nicer plot. So suppose that this is kind of b over k. And this thing here is tangent of ka, looks like this. Something like this, right? Oh, and b over k will eventually go to the other side, I think. Okay, which means what? That there's only some points in which they meet. And these points will be the points that satisfy this condition, which means that they are the points for which the stationary state has allowed values. Okay. So there's only a discrete numbers, a few discrete values of k for which we get a stationary state. Just like in the particle in a box, the stationary states were only these few states. Good. So it's the same here, and what does this tell us? Well, if you remember what K and B are, maybe we can just look at them here. We don't need to take them to the other side. So this depends only on the energy. B depends on the energy and on the potential at this point. And what's the only other factor is A, which is the length of the box, or double the length of the box. Okay. So depending on the length of the box and the height of the potential, then this curve here will go up or down. And this curves here will get more or less spread, which means that we'll get a different number of points for valid values of energy that are allowed in the stationary state. Good. This is for the symmetric case of symmetric wave functions. Now let's do the anti-symmetric case, and you'll get more or less the same. Okay, so this is symmetric case. Let's do here too. So there, let's just copy this. So this is when this and this are the same, but with opposite values. So you get EIKX minus E minus IKX, which is just a sine function up to a constant. Okay, so here. Sine, and we also need a minus sign on one of the exponential bits. Okay, then we do again the same analysis here of continuity. Let's just copy it. And what's the difference? Well, here you get sine. This is the same, and here you get cosine. And no minus sign. Okay, and we do the same thing again. So the second time we do it, it's no longer clever. So we do 2 divided by 1 to get rid of some of this constants, and we get minus b equals k, and cosine divided by sine is the cotangent of Ka. And we'll get again a very similar behavior to this one here. So we get limited, a discrete number of allowed values for E. Okay, so conclusion from both sides is that allowed values for the energy correspond to energy such that B equals K, tangent of Ka, and then we know that we'll have an even solution, meaning and here we have an odd solution. Okay, now if you want the exact values, we need to actually replace all the variables here, all the K and B, and actually solve this equation if we want to find the exact solutions. And at this point we already got most of the insights we needed. At this point is more crushing numbers. So I think you did this in the tutorial, and it's in the book if you want to see it. But I can just show you, first of all, what the allowed values are, and they are these. So copy. Okay, this is done with a change of variables, but it's again the same behavior, right? Where this is what was on the left-hand side, and this is what's on the right-hand side. So this is, this corresponds to the tangent, and this one's to the cotangent. Okay. So they correspond to the even solutions and the odd solutions, and there's only a few allowed values. And this Z is just Ka. And the Z0 depends on the potential. Okay. And again, the number of solutions will depend on the size of the box in all dimensions. So there you go. Okay. Because if, you know, maybe for a small box, this thing will hit 0 before, when there's only a few allowed states. And for a wider box, then it will take a longer time to hit 0. So you get more of this, more of these allowed states. And what do the allowed states look like? I had a drawing here somewhere. There you go. Okay. So let's just call this n equals 1. The first state is like, it's this very symmetric. Just a cosine, we just go once around the box. And then the second one is like the sine function. It's an anti-symmetric one. So this should be, n equals 2, and it's not super well drawn. And this should be n equals 3, and so on and so on and so forth, right? Until at some point, we get that the energy of the particle is higher than the box, right? And then we'll no longer have bound states. Then we start having these scattered states, right? That go just have a higher, a lower frequency here, and then a higher frequency there, and then a lower frequency there. Okay, good. So for more details on this, we look at the book. Again, another interesting thing is that when the box becomes higher and higher, taller and taller, this potential becomes higher and higher, then you get to the limit of the particle in the box that we saw before. Where these wave functions, the bound states will start to look exactly like the ones that we saw. So more like the cosine, and then exactly the sine and 0 outside, like we saw for the infinite potential. Okay. And that's all I want to say for now about stationary states in 1D. And now we will start with the more information theoretical part of the lecture. Okay, so new part of the lecture. And we'll talk about how we model information and ignorance. In quantum mechanics. Yeah. Okay, and I will motivate this first. So suppose that for some reason you don't know exactly which quantum state you have. Okay, maybe a friend of yours gave you a quantum state in a box, and you know that they threw a die to decide which quantum state to prepare, and you know that the die is fair, so you know that it has 1/6 probability of being a number of states, but you don't know which one it is. But you still want to make, you know, measurements on it or let it evolve, etc. And you still want to have some kind of object to represent the information you have about this state. Just like if it was, if you're just trying to model the outcome of the die, then you'd use a probability distribution. If you know a bit more, then you can use a random variable, etc., etc. And the question is, how do you do this for quantum states? Is there any special object? And there will be. such a special object. So let me just see. Here it goes. Okay, and now because we have this technical problem, I'll repeat this whole section from here, if that's okay. Okay. So the idea of modeling information or ignorance is this idea that we have a machine that could produce some state psi I with some probability pi. And it doesn't matter what the behavior of the machine inside is. We're only interested in this output behavior. Okay? And then later on, we might want to measure this state. So either measure it directly, or we want to evolve this state, and there's some unitary and there's some Hamiltonian, and then measure it. And the question is, what is the relevant mathematical object that represents this whole situation here, which we represent by, well, all the states and the probabilities. So what are the desired properties? It should give us the right predictions, and it should be consistent under evolution, under physical evolution. And what does it mean to give the right predictions? It means, well, if I do some measurement and I want to know what's the probability of getting X in this scenario, what I do is just the average for each state, each possible state. I think about what's the probability of getting that outcome when I measure this state, and then I multiply by the probability of having this state in the first place, and then I sum this all. And the same, if I have some way to represent the evolution of this state, which I don't know what it is yet, then if after this I do a measurement, then it should again give us the same behavior. So the probability should be just the weighted average of evolving each of the states, and then doing a measurement on each of this, taking the probability of that, and then multiplying by the probability of having this state in the beginning. So this just means we want an object that is compatible with what we know of probability theory. Okay. And then we wanted to recap what we know about measurements and the probability of getting an outcome. So as we saw, we can represent a measurement by either projectors or observables, where we just have one projector corresponding to each outcome X, which is not necessarily position X, it's just any outcome, depends on the setting. And the observable is just the weighted sum, where the weights are given by the labels corresponding to each possible outcome, right? And so this is a matrix where this is a series of matrices. Okay. Then we saw that the probability of getting a given outcome X when we measure the state psi is given by this, right? Which in the simple case where psi X was just a projector into one state, then this gave us psi X squared, right? Because we just replace here. Good. And now the trick is saying that, well, this will correspond to the trace of a matrix, and the matrix is psi X. So what is the trace of a matrix? The trace of a matrix A is just we take a basis. So we take K to be an orthonormal basis. And we just do this sum. So this corresponds exactly to having the matrix A here and just taking all the elements in the diagonal and summing them up. Okay. And now we can see that this is indeed the same, because we can choose for any pure state, you can choose the basis psi I. Well, let's call it psi j for now. where psi1 is just my state, and then all the other states are so psi j psi is just delta of 1 and j. Okay. So it's an orthonormal basis where one of the states is precisely this state. Then we have that trace of pi x times this thing, and it's going to be the sum over j of this phi j pi x chuk j. But then the only surviving term on this side, we know that this is just delta j1. So then the only surviving term is going to be psi1, which is just psi. So we can write just psi pi x psi, and here comes, this is 1, right? Good. So that's exactly this thing here. Okay. So now from now on, we say, well, we can represent the probability of getting an outcome as the trace of this matrix here. Okay. And now we want, before we go on, we need to know some properties of the trace. So if you don't mind, I'll just take 2 minutes to write some properties of the trace before we go to the break, because we lost some time. So properties of the trace, and this is something you can prove. I think you will prove in the tutorial. One is that it's linear. So how do you write this? Alpha A plus beta B, where alpha and beta are numbers, complex numbers. This is just alpha trace of A plus beta trace of B. The second thing is that it's cyclic, meaning that the trace of A, B, C, so the multiplication of matrices, this is the same as the trace of B, C, A. Okay, of just sending this one over there, or the other way around also works. And finally, there's one more that we need, which is its basis independent. And this means, so what it means is that here you could have picked any basis k to do this. Okay, so instead of picking the basis k, you could have picked a basis that is u times k, and here you get u dagger times k. Okay, and you get the same. So this means in particular that trace of u dagger a u is the same as trace of a if u is unitary. Good, and these things are going to be important for us. So now we'll take a break and see you again at 10. All right, so let's go back. we saw how to represent the probability of getting a given outcome as the trace of a matrix. And this matrix is given by our state here, the cat and the bra, and the projector. And then I just told you that the trace has some properties, so you will prove them in the tutorial. And now we go back to our problem. So we wanted consistency across good predictions. So remember, we wanted predictions to be right. So we wanted that the probability of getting some outcome was given by this thing here, by the weighted sum of the probabilities of getting some the outcome for each of the actual states that are prepared, which makes sense. So now we just replace it with the probability of getting x. So this is a trace of pi x, check, 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 psi I, psi I. Okay. Well, but as we saw up here, the trace is linear. So we're going to use this property to kind of simplify this expression. So we get trace of what? Sum of I pi x psi I. Okay, and now this projector does not depend on I, so we can take it out of the sum. So we just put the px here, and then we have sum over I. Okay, the idea being that, well, this is just number can go there, and then the sum can also go there. I pi. Now, what kind of object is this? So this is a matrix, right? This is the matrix that has just a 1 here. If you write it in the basis pi. If you write it like this state corresponding to psi I, and all of this is some psi I orthogonal, okay? Then it's a matrix like this. And so if you sum a bunch of matrices like this, these states do not all have to share the same basis, but what you get is a sum of matrices. So this whole thing is also a matrix, is what matters here. And then we just give it a name. Let's call this row. So you get trace of pi x row, okay? This row is what we call the density matrix. And the word density here does not come from like density of a liquid or some material. It's density of probability, okay? Because it's given by these PIs, and you know, if the machine produces different states with different probabilities, and these probabilities are not continuous, then this becomes a density probability distribution. Good. So this is a density matrix. Again, it applies for the discrete case or the continuous case. And in this case, in order to know the predictions, you only need to know what the density matrix is and the projector corresponding to your measurement outcome. Okay, so this is kind of our candidate object for representing this situation that we saw here, for representing this situation. Okay, but now we still need to see what happens if we evolve it. All right, so after evolution, and this evolution is represented by, well, we take it psi I to u I. We want that, but that is what? Let's call this psi I prime. Okay. So this is, again, like we saw, sum on I, pi, trace pi x, and here this psi prime. Right, so this will give us, this part here gives us the probability of getting outcome x when we measure each of the evolved states. So we just replace with each evolved state with this version. So just have psi I, pi, trace. Here's my projector. And now this is u I. And this is psi I. Because it's the complex conjugate, transpose conjugate, then you get the u dagger there. Good, and now again we use the fact that the trace is linear to put everything inside. And again, this pi x does not depend on anything, so you get trace of x, sum over I, pi, u, psi I, u dagger. Okay, but now again, well, this u does not depend on anything, so we can also take this u1 out of the sum, and we can take the u dagger out of the sum as well. So we get trace of pi x, and then what? U, the sum, pi, and then u dagger. Well, now this was just rho, right? In the middle, so we just replace with rho, pi x, and then I have u, rho, u dagger. Okay. Which means this is what? Now this is, what color did I use? This is the kind of the evolution of rho. So that means that rho under some unitary evolution u goes to u, rho, u dagger. Okay. In the case of a single state, we could do it like this, just a u there. But because now this is a matrix and not a vector, we also need the u dagger on the other side. Okay, but we just derived it. So let's look at some examples. Of this. So let's suppose that we have a machine that prepares qubits. Okay, and in the first case, case 1, it prepares either qubit 0, 0, or 1 with equal probability. Okay. So then what is rho? Well, rho equals 1 over 2, 0, 0. One over 2, 0, 0 plus 1 over 2, 1, 1. Right? This was just the definition we saw before. But this is 0 plus 1 is just the identity, right? So this is 1 over 2 times the identity. Okay. Let's take again a qubit, but now let's take a machine. It's a completely different machine. It outputs either state plus or state minus with the same probability. Okay, then rho is going to be 1 over 2 plus minus. But you know, plus and minus also form an orthonormal basis. So this is actually also 1/2 times the identity, which means that, let's call this rho tilde, it's different state. So in this case, we have that rho equals rho tilde, right? Which means that if we make a measurement, the probabilities of the different outcomes are going to be the same in the first situation and in the second situation, because we saw that they only depend, you know, they only depend on the density operator, right? And if we evolve them, there's all the evolutions only evolve directly at the density operator, and then if you make a measurement, again, it's the same. So if the density operator is the same, this means that in practice we cannot distinguish the two situations, okay, under this kind of measurements. Okay, under measurements on the qubit or evolutions, which is very strange. So this is a very quantum phenomena. If I give you 2 dice, okay, and I tell you the first one, you always get outcomes 1 or 2 with equal probability, and the second one, you always get outcomes 3 or 4 with equal probability, okay? So you have like 4 different possible outcomes, 4 different states, and in one of them you'll get 2, in the other one you'll get 2. You throw the die once, and you immediately know if it was the first die or the second die, right? But in this case, I give you 2 dice, two machines. This one produces state 0, 1 with equal probability. This one produces state plus or minus. These states are very different, right? They have some overlap, but they're very different. And the idea is that you can never tell which of the 2 dice it is. You can never tell if I gave you the first machine or if I gave you the second machine, if all you can do is measure the systems that come out of it. So this is a very, very particular quantum behavior. Good. So I'll write here some properties of density matrices, which you will need properties of density matrices, which you'll prove, I think, not this week, but next week. So the first one is that it's an endomorphism on H, which really means like a matrix acting on X. So it's an isomorphism within the same Hilbert space, but they're a matrix, okay? That's essentially what you need to know. The second one is that the trace of rho is always 1. Right, because of the way we built them. So we start with the states, each of the states is normalized. The probability distribution is also normalized. In the end, you'll see that this is the case. The second one is that they are Hermitian, so rho is the same as rho dagger. And as a consequence of this, well, no, not as a consequence, additionally to this, so it's positive, which means that it has non-negative real eigenvalues, okay? All eigenvalues are larger or equal to 0 and real. So normally we call the space of density matrices, we can density matrices, we can call it like something like S. I have not looked what the book calls it yet. Okay, which is just a subset of endomorphisms on H. It's a subset of all square matrices. So it's the ones that are also Hermitian and have trace 1. Okay, and because they're Hermitian, they allow for to be diagonalized, so we can have a spectral decomposition. It's called. What this means is that rho is some U, a diagonal matrix U, dagger. Okay, and which means we can write it diagonal, and it's like you can write it in the basis, some basis psi I. Okay, not necessarily the same psi as we saw before. Well, let's call it psi x. It means that we can write rho always as a sum on x of some I'll tell you what this is in a moment. Where so this px forms a probability distribution, and then we have here the eigenstates of this matrix. Okay, so you can always think of rho as being seen as a probabilistic mixture of these states that we will call pure states. We'll see this in a moment. But now note that this is, you can look at it and say, oh, this is trivial, this is where we started from. But no, we didn't start from this, because in this case, when we started off, these states here don't need to be all orthonormal. They can have some overlap. It's just a generic description of like, this machine gives me some states. It could give 0 with some probability and plus with some other probability. And what we worked out is that even if they're not all orthonormal, there is a representation of my matrix that has just orthonormal states. Okay? So this is like a nice way of looking at the density matrix, of interpreting the density matrix. But again, it's just an interpretation, and like, well, interpretations, it's flawed. So let's look at some special cases. Well, if rho is just one state, then we call this a pure state. This is all the states we've seen until now in the lecture. They were all pure states. Okay, so the only relevant object was just one single ket. So we can check if a density matrix is pure by doing, in this case, rho is the same as rho square, meaning rho is a projector. Good. On the other extreme, you have fully mixed states. So this is when rho is the identity divided by the dimension of the Hilbert space. Let's write the dimension of the Hilbert space here. Let's write it just D, and then I say D is the dimension of the Hilbert space. Okay, so this is the fully mixed states we call. These examples that we saw just before, they were fully mixed states, right here. Good. In the case of a single qubit, remember you could represent qubits in the block sphere, and density matrices will correspond to the inside of the block sphere. If a state is not pure, then we always call it a mixed state. And mixed just means we have limited information about it. Okay. So is there maybe a more natural situation than a machine that gives us states at random to think about how we could have ignorance about the state? And there's a very natural example. This is it when we have ignorance about local information. About local information. So, for example, why would this be natural? So suppose you have some joint state, rho B, which is shared by two players. Okay, they prepared it in Alice's lab, and then it's maybe 2 qubits, for example, or just 2 particles, or 10 qubits, and Alice gives some of them to Bob. So these are shared by Alice and Bob. Okay, so system A is for Alice, and system B is for Bob. And Alice only has access to A. Okay, so remember, the way we say is that this belongs to endomorphisms on HA, HB. Okay. But normally we just say it's a state on AB. So how do you describe Alice's knowledge? So in particular, maybe she knew even the initial state, but then she gives some to Bob, and she doesn't know what Bob did on his side. Maybe he did a measurement, maybe he put it through some Hamiltonians, applied some gates, whatever. She doesn't know what Bob did on his side. So what does she know? So we're looking for a map which we call the partial trace. Which will go from the state, so in particular this belongs on the set of density matrices from the states on HA, so this should be normal brackets, tensor HB to just the states on HA. So it should map from rho AB to some representation of Alice's knowledge. She only knows what she has in her subsystem. So what properties should it satisfy? Should satisfy the following. 1, local measurements on Alice's side should yield the correct statistics, right? Local measurements on HA, correct statistics or predictions. On the other hand, local evolutions on both sides should not be detected. On HB. Okay, so let's just look first at local measurements. And it helps maybe to write the full state, to make a little drawing. So we have here somehow the state rho AB. We do nothing on Bob's side. And we want to measure here something on Alice's side, right? Okay. We know how to deal with this, more or less. We've done this before, right? So And what we want the statistics to match. So we want that the probability of measuring X on row A should be the same as the probability of measuring X, but looking at the whole state. Okay. So this is going to be some trace of my pi X. So the measurement is represented by pi X on A, or if you want to look at the full measurement, you remember it was pi X times the identity on B. Okay, this pi X is on A. In fact, just to make it easier not to confuse the two, let's put the outcome here in the subsystem below. There we go. Okay. So, and then I want what I want is that this is the same as a trace of what? Pi xa times the identity on B rho AB, right? This is what we saw before. Okay, so now one way to solve it is to just replace this trace with what it actually does. Right. So let's do it. So let's say we need to take a basis on the two systems and put here. Here's a basis for the two systems, that is decoupled basis. Now comes a thing, pi A X times B, rho AB. And now comes again I on A and J on B. So okay. So now, you know, we know that this acts only here and this acts only there. And then vice versa on the other side. Not vice versa, the same on the other side. So you get sum over I, J. And here what we have is I, X, tensor, J, identity on B. Then this whole thing multiplied by rho AB, I on A, J on B, right? Okay, how do we simplify this now? Let's simplify it for the case where this is just a single value projected into a single state, and we take the I basis to be this very basis, okay? And in the cases where the X is more, where this projector is actually a sum over X's, we can do the same, we can apply the same analysis, everything is linear, everything goes through, but it's just a bit more annoying to look into here. Yeah. So then we have sum over, say, X prime, J, X prime, X, X, times some J, identity over B, rho B, X prime, on A. Okay, this is all A. This is B. Okay, so we're just looking at the special case. So this gives us what? Here we have the delta of x prime and x. So we will get our x prime, our x can go here. And then we have a sum only on J of what? It's going to be identity on A times, well, just J here on B, rho AB, x on A times J on B. But again, this x on A times J on B, we can pull it out and just say, well, this is the same as having an identity on A here, and then having this whole thing multiplied by x on A. Because if we keep track of the systems inside, let's just do this. So this lives in A times B, okay, in S of A times B, say. You know what I mean? Here is the Hilbert spaces of A and B. But now when we apply this thing here, so this kind of contracts the B part, right, to give us a number on the B part, but there's still something left. So this is going to be on S of A, where by A I mean HA. And then when we then contract with that thing there, then this is going to be just a number. Okay. Yes, so it all kind of worked out. Good, so now, well, let's just copy the relevant parts. See if I can do this. I can't. Okay. Okay. We have this. I will put things up later. Good. But what's here on? Let's call just this row A. Okay. If we call this row A, then what we have here is indeed X row A X, and this is the trace of XX row A. So it works out. Okay. You can see that for the case where this projector is not just a single stage, you can do it. It's a bit more complicated. So this step here is not as easy, but it still works out. So what we did here was therefore to say that, well, row A, which is trace B over row AB, we just define it like this, okay, as a sum over J of identity on A times J B, row AB, identity on A, tensor J on B, where these J's just need to be any orthonormal basis. Yeah. Which is in spirit, and I don't want it. So in spirit, which means it's not proper maths, but it's kind of the idea. It's like taking the partial trace over B and doing nothing on A. Taking the trace over B and doing nothing on A. Okay. Okay, so this was the function, this was the map we're looking for to represent Alice's knowledge. And this is a candidate, okay, because it gives us the right predictions. But we still need to see what happens, remember? We still need to see what happens here under local evolutions on HB. All right. Let's see, to local on HB. So what we want, in fact, is that we cannot detect them. So suppose we have row AB and it will evolve through something on B side. So this means I have here row AB, I do nothing on A, but I do some kind of evolution on B. Yeah. But then I only want to look at the part at the row A here. Yeah, I want to take the partial trace and look only there, and I should not detect what is happening on B. So what's the global evolution? Well, we saw it's represented by, yeah, we can do even more general, and we can look at, well, let's say I do some evolution U on A side and V on B side. Let's do that. And I should only be able to detect the evolution on A. So we do this, row AB, and here UA dagger, VB dagger. That's V. Okay. And now let's look what happens when you take the partial trace. So this is row AB prime, we call it. So what's row A prime? This is going to be partial trace over B of row AB prime. Okay, so which is the partial trace over B of this whole thing. VB, row AB, EA, VB. Okay. So what is this? Sum over I and J of this thing, right? I on A, tensor J on B, this thing here, VB, row AB. Oh, there's some daggers missing. UA dagger, VB dagger. And now comes A and J again. And do you know what we can choose? And this is kind of a semi-clever trick, but it's kind of natural. So we can pick any basis for these JBs, right? So let's just pick the ones that kind of reverse the unitary. So let's just say that pick J, which is equals to some V to this VB dagger and some other basis, J tilde. Okay. So we just replace this whole thing. I, J dagger. Well, J, I, and G we have. Well, we can already put that the, no, let's write it here. I, now we have this J tilde. V tilde, V dagger B. And now we have here UA times VB, Rho B, UA dagger times V, B dagger. And now we have here I on A, and here we have V, B, J tilde. Okay. So now we just act with them with the tensor product. We know that this act's only there, and this act's only here. This act's there, this act's there. So we get the sum over I and J of what? I UA times J tilde, and now this VB dagger VB. This is just the identity, right? They cancel out. Rho B, and on the other side it's going to be the same. So you get UA dagger times VB. Oh, sorry, I VB dagger VB J tilde. Okay. Which means that we can get rid of this. And this is just one way to see how it's going to work out. Okay, we can also choose, well, this, sorry, what did I do? Why did you let me do this? We saw it was the partial trace we were looking at, not the real trace. So this could be the identity on A. Identity on A, identity on A, identity on A, and here the same up here. And all the sums are just over J. Okay. Identity on A and identity on A. There we go. That's much better. Okay. But this is just, the A does not depend on J, so it can come out again. So then you have UA, and then you have what? Sum over J of this thing. UA times J tilde, Rho B, identity on A, and here J tilde again on B, right? And we put the UA dagger outside. Yep. So this is just UA. This thing here, well, because this basis J is just any basis, right? Any orthonormal basis, then this is, like we saw before, this is just a trace over B of the initial state. So this is just Rho A, UA dagger. Good. So that's what happens. So Rho A evolves as this, which means that if you have local evolutions, you can do the following. So you can start with Rho B, evolve the state with UA and VB to have this thing of UA VB first, UA UA dagger times VB dagger, and then take the partial trace over B, and then you get this UA Rho A UA dagger. Or you can do the simplest thing of taking the partial trace first you get just rho A here, and then it just evolve it with UA and end up in the same solution, right? So this diagram is commutative. Attention, very important, you cannot do this if the global evolution is not of this form, is not a product of local evolutions, right? If I give something to Alice and something to Bob, but then I do something, I evolve them globally, then you will see a difference in rho A. But as long as you only do some change on Bob that's independent of the change on Alice, that Alice cannot detect what's happening to Bob. And this is also called the non-signaling principle, like we saw before. Good, so we'll stop here. And then in the next lecture, we'll see now how to model uncertainty, not just about states, but also about the evolution itself. Good, so we'll stop here and see you on Thursday. Bye.